Okay, so good morning, everyone. So today we have the second lecture of homework on conjecture and union of tube and KKS.
Thank you very much for hosting.
So today I'll talk about the proof of the sticky KKS set, which says the following. This joint with from Josh. So if a set of delta two is sticky in tension, and for any TNT, let's say YT is. I'm presenting a slightly stronger version that's more flexible for pigeonholing, but for you can just think YT as the T itself. So it won't change the intuition, but it just helps to make the things rigorous. The YT is a union of delta T. And we have it's almost the same as T. And the union of tubes. So this is defined as union. There's a delta the epsilon times the number of tubes times the volume of one tube. So this says that any sticky set of delta tubes in R3, they are essentially disjoint. And thus, recall what's the definition of stickiness. A set of delta tubes is sticky if for any signal between delta and 1, the set of T rows, the covering of the delta tubes satisfies the test-out convex Wang, which means for any convex set W, the number of row tubes containing W is bounded and approximate by the volume W divided by the volume T row. So this definition makes more sense when everything is roughly uniform in the following sense. So there is a simple pigeonhole lemma says that for any set of delta tubes, there exists a significant fraction T prime, such that for any intermediate scale row between delta and 1, there exists a set of distinct row tubes covering the T prime, the subset, and each T row contains roughly the same number of delta tubes in T prime. So when we think about the definition of stickiness, we should think about after applying this lemma, the T in the definition of stickiness should really be the T prime, so that we have a roughly the same number of tubes when we zoom in any fifth tube.
So why you think for the word sticky or in the do you mean that the appears to intersect?
Yeah, so this word sticky comes from a paper of Kessler. In their original in their paper, the stickiness means the following. So in their paper concerns of a set of delta tubes satisfying the KKR assumption means that it contains a delta tube in every delta separated direction. And when the sticky means that the delta tubes in nearby direction, they stick to each other. They should also be close and not too far apart.
Not like that.
I'm only talking about tubes in a close by direction. They're not like that. They should be like this. But that notion is that notion was also worked in our paper initially, but that this notion is not very easy to generalize. And we realized that it's costs almost nothing for us to this more general notion of stickiness and obtain the same result. And this is a definition that enables us to extend to the general class. But we still use the sticky juice because it was this is an important concept, and all the, as I said before, all the main proof strategy at the beginning was due to cats and dogs when they continued when they had thought a lot about this those carcasses in three dimension space in around the 2014. I will just make a quick note about this shading, and from after that we'll just ignore the shading and consider it as the same set of tubes as the whole set of tubes, as the whole T. The reason why I want to put the shading, this Y is called shading, YT. The reason why I want to put it here is just to make the following definition rigorous. So this is an important quantity that we are going to find. The multiplicity is the number of tubes. So one should think the multiplicity as the number of tubes passing through a typical point. But what does it mean, a typical point? The use of this shading is like after pigeonholing passed to some significant subset of the tube. This is rigorous in the sense that it is literally for every point in the union of the shading, the number of tubes passing through each point. So this is number of data tubes. So what we do is for each of those points, we find the multiplicity, but means the number of tubes through it, and then we pigeonhole such that we pigeonhole it so that we find a popular multiplicity, and that dominates. That dominates them. Let me just make it rigorous. So for n, so we can find them average needed and remove instead the collection of x such that the number of tubes such that x is equal to t is roughly needed. And then we find a dyadic mu such that mu times mu is roughly, and then we define y prime t as mu intersect y. And from now on, this multiplicity is really the number of tubes through each point. Through means that YT contains X. And also there is just one last comment about this pigeonholing steps, so that you know it's something that we can make it really rigorous. It's let's say Y1 is a step shading of Y. And Y1 heat is greatly approximate than mu T Y1 is greater approximate than mu T
So this is also just by. So sorry, I should here it should be but it's approximately the number of tubes times t. The reason is just that since y1 is a subshading, so the union of y1 is subset of the union of y, and that's why this passing to a refinement, the multiplicity dominates the original multiplicity. So all I want to say is that in the rest of the lectures, we are going to do a lot of saying that after some pigeonholing and passing through some refinements, and all this is okay because upper bounding the multiplicity of the refinements is like upper bounding of the original multiplicity. And from this, we know that even put upper bound as on the union of shading, which is even more than better than the lower bound of the union of the tubes. So and now from now on, I'm going to drop the y and just hope to convince you that all the pigeonholing steps are rigorous. Are there any more questions? I know this is a little technical, but I just want to quickly go through it in case some of you really care about the rigor. So I'll drop y from now on. Okay. So this mu makes sense between, let's say, 1 and delta to the -2. So we can choose a dyadic number mu.
Here is the number.
Yeah. So this mu just means the number of tubes T such that X is in YT. So the proof sketch, let's let sigma be the smallest number. And with dt, the multiplicity is bounded by number of tubes to sigma. So sigma equals to 1 is trivial. So it cannot be really smallest, but goal is to show that sigma equals to 0. And another comment is that, so here, since a set of tubes is sticky, means the tube itself satisfies the Kastau convex Wolf axiom. So it means that the number of tubes is less than delta to the -2. And also, this sticky definition also means that this T rho is sticky. And for any T rho, the set of tubes containing T rho after rescaling is sticky. After rescaling means that we rescale the set of tubes containing T rho to a set of delta over rho tubes. So this means that the local stickiness behaves very well on the thickening and also on the restricting to the tubes inside a thick tube. We are going to use that and to study the multiplicity of tubes at many scales.
So can you say again how you think of YT in the theorem? So T is just a delta tube, and YT is mu delta tube.
So this YT is really coming from, let's say, at the beginning, let's just consider YT at T itself. At the beginning, this multiplicity, it just means a number of delta tubes through a typical point, right? But what's the meaning of typical? Because there maybe some point has a lot of tube passing through it, and some points
as a 1-2 passing group. So the introduction of YT is saying that, okay, we can apply this visual holding to find some subset of tubes such that each point in the subset has exactly the same number of tubes passing through it. And this YT is like a 1/log delta fraction of the previous T. But in practice, this YT, we allowed it to be slightly more flexible. Let's say it's delta to the eta power, where eta is extremely small, and to allow some flexibility in the proof.
I was just a bit confused because T is a delta tube and YT is included in T.
Yeah. So YT is just a fraction of delta force. Some subset of some subfraction of delta force inside 1 tube.
So YT is not a delta tube.
Yeah, it's not a delta tube, but it's like it almost fills out the
delta tube. So okay, I was.
Sorry, delta force. I'm really sorry.
Okay.
I'm really sorry about it. Okay. So assume that the sigma is greater than greater than 0, then we can find the extremal set of T such that the multiplicity is roughly the number of tubes with a sigma. And we are going to work with this extremal set. Also, without loss of generality, we can assume this extremal set has cardinality roughly delta to the -2. The reason is that for any sticky set, one can take some number of rigid motions such that union of some union of some translation of rotation of T. This together is again sticky and has the maximal cardinality. So what I want to say is that it's harmless usually to assume the number of tubes in the sticky sets is roughly delta to the -2, and this will make our analysis a little easier. Okay, so there are a few steps. The first one is to show T row, and this after rescaling, they have a rescaled version of tubes containing T row at extreme. For any row, we can multiply one. So this just means that the extremal just means that all multiplicity also saturate this bound mu. So the mu T row is roughly the number of T row to the power sigma. The second step is to use the first one to show that the union of tubes organized into slabs. So previously we think about a union of tubes. Now using the first consequence, they are going to organize. They are going to become a union of little slabs, and then this will give us some reduction to some products. And the third step is to use projection theory to analyze some products. Some product formula that coming from analyzing the interaction of those slabs at different scales. So the first and the second steps are
we are basically following the outline in Task law. And the third step, we are using more recent tools in projection theory. And it's also the third step that one can distinguish the real numbers and complex numbers, and therefore rule out the bad example in C3 that we discussed. So now let's go to the first step. And I should also say that the first step is kind of is somewhat general. This first step is usually the first step in the study of sticky sets in other settings as well. So we're going to look at the first step carefully. Since we are going to study the multiplicity, and we can So we can compose a multiplicity of tubes at one point. According, like we regroup the tubes through this point into tubes contained in some low tube. So this is low, and then we have mu is the pigeonholing. It is roughly mu t inside t low times mu plus mu g, and those g's are this segment of length delta over rho for this g. The g comes from, I will use this blackboard G to denote the collection of G. The G comes from the fact that if two tubes inside one row tube they intersect, they stay intersect for a while, and they intersect into a tube segment of length delta over rho. We also have the following bound. This is from Wang. The second bound is just the number of tubes through one point is bounded by the number of tubes inside one row tube through one point and the number of row tubes through this point. So the first bound is approximately equality after pigeonholing, and the second bound usually it's not very good. Especially in the non-sticky case, the second bound is usually very lossy. But the whole point of stickiness and the extreme example is to show that, in fact, for the extreme example, the second bound also has to be sharp. So we said previously, if a set of tubes is sticky, then T row is also sticky. The set of row tubes is also sticky. So this term is bounded by number of T row to the sigma. And the row tubes contained in the delta, the delta tubes contained in the row tube should also be sticky. So it's also bounded by T row to the sigma. And previously, the lemma I just erased tells us that this whole thing is roughly number of tubes. And since T is extremal, this is also number of tubes per sigma. So we have a train of inequalities, but the left-hand side and the right-hand side, they equal. So this means that every inequality here has to be equality. and this tells us a lot. So this two equalities means that these T row and the tubes inside T row are extremal. And this inequality become equality tells us a lot of things. It says that if say this is again true after pigeonholing, but this become equality means if T row intersect union of tubes non-empty, then the accusation. If X is inside then there exists P in zero passing through X. So this is the key observation for analyzing sticky sets in many settings. So what does it mean? It means that previously, suppose there is one point here that lies in the union of tubes. And there are a lot of other road tubes. There are a lot of road tubes passing through it, but sometimes, for example, this road tube passes through this point, but sometimes it's not guaranteed that the delta tubes in the road tube also passing through this point, so they might miss it. But the fact that this two agrees says that it's very unlikely for the delta tubes in road tubes in this road tube to miss it. It has to almost surely pass it through any point. And this allows us to, we'll see it very quickly. This observation allows us to say that the union of tubes are in fact a union of two-dimensional slabs. And this is what we call the gradients. It's a cat and Lapine top gradients. So maybe so this is just very simple chain of inequalities and get this powerful consequence. Are there any questions about it? Okay, now how do we get the gradients? How do we get the union of slabs? So as we see before, I'm just looking this picture. So in this picture, we know that those. Okay, maybe let's first think of the special case where rho equals to delta below 1/2, and so that there's two numbers agreed, and we don't have to deal with two different side lengths, two different lengths. And this delta tubes inside this rho tube intersect in a segment, and this segment is contained in this rho tube because we put rho equals delta to 1/2. And then since it's contained in this rho tube, all the points, other points that in this segment will have another, we'll have some delta tubes in this rho tube passing. So let me adjust. So this segment is coming from the intersection of delta tubes in this row tube. And since it lies inside the other row tube, for any point, there should be some delta tube passing through it. And the delta tubes, they have to lie within this row tube, so their direction is with an arrow of row pointing towards this row tube. And this means that this whole collection of segments that looks almost parallel, and we can just move the segments so that it fills out this slab. And each of them coming from some row tube, they might have different directions, but they all lie in this row tube. So any such intersection will give us a slab. Slab now means delta to 1/2 times delta to 1/2 times delta. And a consequence of this means that union of tubes becomes union of more like this union slabs. And moreover, we know that inside the same delta to the 1/2 ball, this is a union of parallel slabs. So all those important geometric consequences coming from this simple observation.
Yeah, but why delta? What happened with the rho?
I'm taking rho equals to delta to 1/2.
But then can you always reduce to that case?
So this holds for any rho. We can take rho equals to delta to 1/2 when we want to obtain the second this slab decomposition. Are there any other questions?
Well, you really don't care what happens between delta and delta 1/2?
I will care later, but at this stage, let's just focus on rho equals to delta to 1/2.
So your chain of inequalities, there are inequalities with each twiddle, right?
Yeah.
So the thing you obtain in the end is this twiddle doesn't bother you.
Yeah, I'm hiding a lot of pigeonholing. So and also the shading means that it's not the entire segment, but some like delta to the absolute fraction of the segment. And I'm hiding all this.
So it's up to smaller sets.
Yeah.
So what is the loss? So you get huge number of losses. What is the losses that you allow to lose? I mean, what are the losses that you can discard? What is your rule for discarding all these losses?
Yeah.
I think that they are of what size?
Yeah, that's a very good question. So so the number of steps that we are going to do is so let's say imagine in the end we want to have something like union of cubes greater than to the epsilon number of tubes times the volume of tube. I think once this epsilon is fixed, the number of steps that we need to do is some constant only depending on epsilon. And then previously I said this yt is greater than something. So in reality, what we use is greater than delta the eta t, where eta we are allowed to choose as small as possible. But something that we really need that comes out from pigeonholing is this yt could be smaller than 1/delta. So the up to some small sets, the small sets could be as small as 1/log delta fraction. And sometimes since we do a lot of pigeonholing, this will just accumulate a lot. But in the proof, we realize that it's also okay to assume this power loss as long as eta is like extremely small compared to epsilon. Okay, so the reason why this has to be parallel. So if we have only two, then this will lie in the direction spanned by the two road tubes. But there might be some other road tubes. And what happens? So if there is another road tube that goes towards the blackboard, goes inward, then this observation will tell us that for each point on this slab, there should be another segment that's going inwards the blackboard. And then this will give us a three-dimensional cube. So we're extremely happy because this tells us that locally this union of tubes is three-dimensional, and then we can just pick on it and apply induction. And this is the reason why this observation, plus the fact that it's an extremal set of tubes, meaning that we cannot get it any better than number of tubes to sigma, tells us that all the road tubes passing through this wall at this point has to be essentially coplanar. As long as it's not coplanar, then we can get little three-dimensional cube and we're done. So this really tells us a lot, and this is why it guarantees that the union of tubes intersecting the delta to 1/2 ball has to be a union of parallel slabs. And from now on, we can see the structure of this extremal CB Kk set. So let me just draw the picture. This, I'm going to focus on only one road tube. We have to go back to different road after, but let's just focus on road equal to delta to 1/2. And in each delta to the 1/2 cube, it's a union of slabs, and the slabs should also be parallel to the direction of this road tube because that's how our slab is formed. It's formed by the span of the direction of road tubes. But we still have a one-dimensional freedom because like suppose this road tube points in a vertical direction, then we still have a one-dimensional set of freedom to rotate the slab. And here it could be like this, but they all have to be vertical. Yeah. So this is there should also be the road tube that's the delta tube sets are passing through it, and then when they intersect this slab, they have to intersect it tangentially. So now this is the structure that we get from this train of inequalities. Well, are there any questions about it?
But why it's completely filled? Why don't you have jumps between the upper bound?
Which
I mean, why, for example, the second piece, why is there? Why are you sure that you are not missing any of these boxes, these cubes?
in this piece?
Yeah, why they have?
Yeah, so this has to happen if we ignore the pigeonholing. This has to happen everywhere.
Mhm.
So this has to, this is for any x inside UT intersecting T row. So T row, by definition, will contain a delta tube. So at any length, any part of the T row, there is a delta tube. So there is some x, and this x will give us some slabs. And yeah, so this red part is also the hidden structure inside union of tubes in T row. And since we said that the delta tubes in T row after rescaling becomes again a sticky set of tubes. So we are going to do the rescaling here. This is 1. And this is again 1. Now, each of the slab will become a horizontal tube. And there are a lot of them. Middle. So this is again an extremal cassette or an extremal set of tubes that we could apply the same reasoning as before.
But you rescale just in the normal direction? Or?
Yeah, we just, so this is the tube pointing in the vertical direction. We just stretch on the horizontal direction by 1 over rho.
Mm-hmm.
And because the slabs also should parallel to the zero, so the slabs after this scaling becomes horizontal tubes. And so this part is the union of, let's call this T tilde as phi theta. Let's call this rescaling phi. Then this picture is the union of T tilde. And T tilde is sticky and extremal. Extremal just means the multiplicity is again of tubes to the power sigma. And since this is extremal, means that we can apply the same reasoning as before. So this means that we also locally have the following. This should also be locally a union of slabs. So I should say that then this horizontal tubes has side length rho, and those slabs has dimensions rho to the 1/2. Rho to the 1/2 times rho. So this green slabs coming from the same reasoning with T tilde instead of T. And also, before that, let's just recall, write this union of tubes in parameters. So now, since it has the structure that is a union for parallel horizontal tubes, so we can write it as x plus z, y, z, y and z are in 0, 1. So they are not really in 0, 1, but like a fraction of 0, 1 that we are going to the difference. And x now is in some set that b. So each of those horizontal tube, so it's for some fixed z, and this is parameterized as a horizontal tube, and x means the location of those horizontal tube, and fz means the slope or the direction of the horizontal tube. And because they are parallel on each horizontal slice, so that is why the slope only depending on z. And for different slice, this slope could change. And since this is again an extremal Kakeya set, this AZ should be has some. We can write out the size of AZ depending on the size of union of tubes. Okay, AZ is roughly the same as. So this means the measure in one-dimensional, and this means the measure in three-dimensional. They are roughly the same, and we want to show that the AZ has to be large. And this starts to become this parametrization is going to lead us to some product formula. And also this union of tubes is again a union of slabs, and this slab S tilted. It's coming from the same reasoning. Maybe I should pause and see if there are any questions.
Can you say again how you define the green lamps?
So this U tilde is extremal. Sorry, this T tilde is extremal, right? It's sticky because that's a rescaled set of delta tubes containing rho tube. And also extremal because we show that the multiplicity of that has to approximate the number of tubes to sigma. So it's extremal. And that is why we can apply the same reasoning, the first step, with T tilde instead of T. And since for T we get a union of slabs, so this observation and that observation that this union of slabs. So similarly, for this T tilde, we can also get a union of new slabs S tilde, which is at scale rho to the 1/2 instead of delta to 1/2. Okay. And now we are going to. So those previous S after rescaling, I'm going to call it L. Or maybe if you don't mind, we can also continue to call it S, but just the rescaled version. The point of this sum product formula is the interaction between S and S tilde. So first of all, we should notice that. So S tilde has to be aligned. Because this T tilde is both the union of T tilde is both a union of S and also a union of S tilde. If they are not aligned, suppose S tilde is here, like this, and S is pointing like transversely, then at any point there should be an S, and then again we get a three-dimensional cube. So it means that S has to be going with the direction of S tilde. And we call those S as global branes. And tilde as local brane. because S is longer and S tilde is more local, is inside of every single S tilde is inside some rho to the 1/2 ball. And we are going to study the interaction of global brain and local brain to get some product formula. I'm just going to say if in the plane tilde is not empty, then S have to. This is what I mean that they have to be aligned. And second, a tilde in the rho to 1/2 of. And this is because of that this the local brains have to parallel. That's also from what we discussed before. The properties that are going to be needed for deriving the subproduct. The first one is again S, the global brains in each horizontal brain. Again, this is a consequence of those S being parallel, and after rescaling, they become parallel horizontal tubes. So what we are going to do is fix one S. So fix one S. Now, this S tilde, since they are aligned, they look like that. Again, we have something like a one-dimensional set of freedom to move the direction of the S tilde. And we are going to look at what happens in this rho to the 1/2 move rho. The drawing is not great. Sorry, let me reply. Let's say this is an S. This is rho to 1/2, so you can have tilde. And the first horizontal layer, they are all parallel, and then at the first rho to the 1/2 box, the S tildes are also all parallel. But if we move to something higher, then the direction of S will change. Like some higher horizontal slice, the direction of S will change. And then if you move to some later boxes, the direction of S tilde could also change. But this change in something like a vector field, because like it's pointing, there are two vector fields. This S is horizontal, and this S tilde is like pointing up. And we can again do a rescaling. we are going to just rescale there because there are two sides that go to the left. And there is one side that has less than one. So after rescaling, because the picture is easier to draw with rescaling. Rescaling, then so this is again our S. And now each S filter will be vertical. So at the beginning, without loss of generality, we can assume it's a vertical tube. But later it could, and I need more color. We go up to some other horizontal slice. This might change the direction, let's say. Something like that. I hope it's clear. And if we go to some other slice that's like this, then this blue tube will change the direction as well. So it could go this way. But sorry, I think it's still a little messy, but I hope you get it. But are there any questions about this picture? So basically, we have two collection of horizontal lines. One is but we have two collection of lines. The red ones, they are parallel on each horizontal slice, but they could point in different directions. And let's say this direction is right. And this direction is Z. And the blue tubes inside each slice that's normal to Y, inside each XZ plane, each plane that's parallel to the XZ plane, the green tubes are parallel, and then in some greater plane that's parallel to the XZ plane, the blue tubes, they might point in a different direction, but they still lie in this plane and be parallel. And the location of them, both this green tubes and the red tubes, in some fairly small set of this is called AZ, and we expect AZ to be small because otherwise we proved our theorem. So AZ has the same measure as the measure of union of tubes, same measure in the one-dimensional setting. So how can we fit such a thing? Like we start with some very small set, and then we have a lot of one-dimensional. We have a lot of tubes in two ways. They have to all interact and then manage to squeeze themselves in a very tiny space. And in principle, this is impossible. And we are going to see how it's impossible by deriving let them travel. So let's without loss of generality, we can assume the green tubes on the first XZ plane is vertical, and the red tubes on the first horizontal plane is pointing in the Y direction. This is just after some rotation, we can assume that. And now we're going to travel, let's say, from this point, 0, 0, 0. And then we are going to, okay, it should be also convenient to note this as FC 1, 0, because they are horizontal. And the direction of those green tubes, it only depends on y, because on each XZ plane that parallel to XZ, they are the green tubes has the same direction. So the green tube in the let's say they are in the direction dy 0, 1. So these are the directions of those tubes. And now we're going to trace them. We're going to travel from the origin and then to some height d, and then travel along this and we meet some red lines, and then travel along red lines to some coordinate y, and then there should, let's say this coordinate, and there should be another green tube, and we're going to travel along green tube, and then let's say I should really draw 3 layers and then travel along this some red tubes again and some green tube. So we're going to derive some product problem by letting a point should travel along both the green and the red ones several times. It's like calculating the commutator of some vector field. I'm doing it in a very complicated picture, but it's really not that complicated. Okay, let's do another zero today. This direction is that's 1, 1, 0, and green tube that's pointing in the direction of G, Y, 0, 1, and then another red tube that's pointing in the direction of D, 1, 0. So that just travel until y equals to 0, and another green tube. 3 is green, and goes down to 0. So this point is 0, 0, 0, and this point is FC 1, 1, 1. And this point now is FC 1, y plus g, right?
Mhm.
And d1 minus d2, y, b. So this is really just placing the coordinates. At this point, we travel to y equals to 0, that is FC1 minus FC2, y plus d1, d1 minus d2, 0, d. And then going down, just give us this part, the same thing. So what do we get from this is we start from the 0, 0, 0, assuming that this point is in Z. And then we do this traveling, and then we're back to some other point of in A0. Or say, we can. And we might as well start from any other points in A, and this will give us the same formula. So this says that A plus B1 minus B2 Y plus B1 B1 minus B3 is again contained in A. And this is the for M B1 Z2 Y in 0, 1. Again, this has to be not exactly 0, 1 interval, but some let's say delta to a fraction of the 0, 1 interval. So this is the sum product formula that we obtain. And this term we can write it as A plus F minus F. Product is P is containing A, where F is F Z B, and G is Y B1. Z Y and 0. So I'm just rewriting this in more some product like formula. So up to this point, I should say that we still have not yet ruled out the complex space example. Do people see why?
No.
I think you should see why. Okay, so the reason is that for the complex for let's say for the example in C3, we can take A equals to R and FZ equals to Z bar, BY equals to Y complex conjugate. And then we have and then F minus F is equals to and then A plus A equals to 8. And this is exactly the reason why Wolf's estimate is really hard to improve, because A has like half of the dimension of complex numbers, and this corresponds to this AZ has 1/2 dimension, and this corresponds to the union of like the Kakeya set has dimension at least greater or equal than 5 halves. So this is the point that we have reached the point we are going to apply projection theorem to say that since we are in R3, such things are not possible, unless. Also, I should note that there is one case that's, let's say, F lies in this line, so F3 is equal to Z, and G, let's say G lies in the line that's vertical to it, perpendicular to it. This is our F, and this is our G. This is another possibility. So there are two enemies, the first one and the second one. The second one means that F has to be linear and G has to be linear. And so the first enemy is really difficult. And it requires a lot of tools to get rid of that. And the second enemy, we just admit it. So in the sense that, okay, this could happen, but this tells us a lot about F. And in some sense, this is an increased regularity of F. I will explain why very soon. So previously we said that this is E can be written as E can be parameterized as such an Fz. Oh, so what is Fz? From the previous reduction, Fz is almost Lipschitz. So it's not a Lipschitz in the analysis sense. It's more like we can decompose the interval into like the unit interval into dyadic intervals. And if the z's lies in the same dyadic interval, then Fz1 minus Fz2 is bounded by this dyadic number. So it's not a very strict Lipschitz sense like bounded by. So it's not in the sense that Fz1 minus Fz2 is bounded by Z1 minus Z2. This is not true, but it's only true if Z1 and Z2 lies in the same dyadic interval. Actually, this is the fact that this is not true makes our life a lot more difficult, because when we started to work on this sticky Kakia problem, somehow we thought this is true, and then it seems that the problem is really easy. But now we cannot use that, and in fact, the toy model that Larry pointed to us is that this is in C3, but in R3, the F that we should have in mind is the following. So let's say 1 prime in R3 in R. So the F we should have in mind looks like this. So we decompose the unit square. That's the F, like the this F should be like, we decompose the unit square into 4 squares, and we take this part, and then we keep decomposing, but we take the opposite one, and we iterate. So this will be an F that satisfies this like almost Lipschitz assumption, not this one, but the one that's about dyadic intervals. And this is what makes the problem quite difficult.
Excuse me, why is this the toy model?
Because this satisfies the like version of Lipschitz property. Like this point and this point, even though their distance could be quite small, but they lie in different dyadic intervals. So their F, the value of their F is still like bounded approximate by the corresponding dyadic interval size. But this is far away from being Lipschitz. And this also has all the properties that we need, like F is, when you say that, why do we only use one row? But in reality, we should use all rows to deduce that this F is almost self-similar, not self-similar, but like has the same, like almost a deregular, almost irregular has roughly the same size if we zoom in. So this example satisfies all that. And the previous naive approach of assuming that F is just Lipschitz fails for this example. And this is the example that requires us to go to projection theory. Because in projection theory, we deal with a lot of fractal sets. So this example, after iterating, becomes like a Cantor set. So let's say here's some direction in F minus F. Then theta dot G is just the orthogonal projection that we talked about before. This is the direction theta, and then G, and this is the theta dot G after some disturbing.
No, I'm sorry, I'm very lost, of course, but capital F is now a subset in the plane, or this precise line? No.
So yes, capital F is like somewhat like a bar. But since this F, we know very little about it. It only satisfies this static version of Lipschitz. So what toy model is this picture? That's our F. Similarly for G, we can also cook up with some similar example. And so now let's first fix one point in F minus F. And this theta dot product with G is just orthogonal projection. And so previously we talked about Marstrom's projection theorem, which says that for almost every theta in S1 in the circle, orthogonal projection keeps the dimension of G. So now the dimension of G actually here is at least 1 because it's a graph on Y. So we know that for almost every theta in S1, theta about G So I again use this has some loss of delta with epsilon, but I'm going to ignore that. But the key issue is how many directions do we get in F minus F? Again, that is this is the why C is different from R, because in this example, for this example in C, we do not get all the directions. Only get the one real dimensional set of directions. But for F in R2, so here is the theorem. Also, so the question is how many theta. So we only care about directions because this F minus F is a collection of vectors, but vectors in the same direction only counted once. Now, this gives us in this stage. This theorem is drawn with Thomas Opponen and Pablo Schmerting, which says that if so this F is not contained in any line, then there exists P in F such that the radial projection of I, this is I, equals to the minimum of the also dimension F. The radial projection just means that and this is we take all the directions spanned by P and pointing F. So I P Q maps to P minus Q P minus Q. Of course, this has to exclude the point P as well. So this theorem tells us how many directions are there in F minus F. The requirement that F is not containing any line is natural because if F is contained in a line, as this example, then we only see one direction as the direction of the line. And also like this assumption exactly corresponds with this second example that F is contained in the line. So this radial projection theorem distinguishes real numbers and complex numbers because, as we saw, that the same thing in C2 is not true for the same example. And here it says that suppose F is not containing any line, then F minus F determines a one-dimensional set of directions. And here in Marstrom's projection theorem, it says almost every, but this is like too strong. So Kaufman weakened the assumption, says that for any one-dimensional set of directions, there exists one theta such that the projection in this direction preserves the dimension. So I will just say this theta in the So here is here we show that this F minus F dot this G has dimension 1 unless F is contained in a line. And so the second example is the last thing we need to deal with.
Finish?
No, not yet. I have still to finish. I still need to talk about that. Also, I have to until 11, right? It's done.
Yeah.
Right clock.
Just this is what you call projection theory, this theorem, or I don't know what is projection.
Yeah, so this is one projection theorem we use, and next I'm going to present another one that we use to deal with this case.
So it's so it's about what are all the possible projections in one less dimension of a two-dimensional set, or what is it exactly? So I'm not sure what you put for projection theorem. It's how to do an ordinary projection with respect to coordinates, so of a two-dimensional set or a larger dimensional set.
So when I said, so here I'm just, when I say projection theorems, I just mean something in general, like if we have an arbitrary subsetting in Rn, and then we have a collection of, say, small dimensional subspaces, and whether there exists one subspace such that the orthogonal projection of this set onto the space is large. And this is, even though this is a radial projection, but it's like a different variance of orthogonal projection.
That's what we mean by projection theorem.
Yeah, and then we're going to see another one that deals with this case.
How large is the project? Is a random projection of the set already not random?
Depends on what we say. How do we define randomness? Because if randomness uniformly random, then I think it's like the result from Marstrom or Matila to almost every direction. Also, here I said F, but in reality, I lied a little bit because we only study what happens inside this row to the 1/2 horizontal tube, because this is like a row to the 1/2 neighborhood of a global grain. And so this means that all the information only happens when Z is between 0 and row to the 1/2. Of course, we can apply the same thing at all different scales, at all different layers. So what it tells us about FC is that, so this was sort of the enemy that looks very much like the enemy in C. And now, after applying the projection theorem, we can say that this will kill this enemy. So this is if F looks like that, then our union of tubes has a very larger has the desired measure. But now what happens is that F might be locally like a line. So what this says is that the graph of F, now the new enemy, looks like the following. So the graph of F should not be looking like a Cantor set, rather locally is like a line. So it's like contained in a tube because we have some resolution, and this is row to the 1/2. The thickness is rho. And we know the graph of F is contained in such rectangles. This is again because all our analysis happens in this horizontal long box of height row to 1/2. So we only get the information of F Z from when Z is between 0 and row to 1/2. And we can repeat the same argument for other intervals. And this is where we use different rows again for other intervals and for other scales as well. So this means that at other scales, the graph of F lies in some rectangle. Let's say this is of size tau to the 1/2 and tau. And what does it mean? The graph of some function lies in little rectangles at all different scales of rectangles of something of the form like tau to the 1/2 times tau. So this says that this F is C2. So we managed to upgrade the regularity from not even Lipschitz, but something like a dyadic version of Lipschitz continuity to C2. And this upgrade of regularity enables us to apply a different projection theorem to conclude. I will present this different projection theorem that uses crucially that F is in C2. So now we can present a twisted projection. So from the goal is to say that maps E to A to AZ. So how to do that? This is X, Y, Z. This maps to X minus D minus Y. And if we define the twisted projection as such, then this F, this pi F will map E to some very small set in the one-dimensional space. Because E has the form of X plus F, Z, Y, Y, Z. And this under this E is in here, and under this twisted projection, pi F, it just becomes X plus F, Z, Y minus F, Z, Y. And so this two cancels out and gives us an X which lies in AZ. So this twisted projection is some sort of projection that maps. So E is a union of tubes, somewhat large in three-dimensional space, something that's small in a one-dimensional space. So E is essentially the product of AZ times 0, 1 times 0, 1. Another information we have is that E contains a lot of tubes. So let's say E contains a tube. That's like neighborhood of a line segment of the ABCD is A plus C, B plus B, T is contained in P. Then what's the role of what's the image of this line under the twisted projection? This becomes A plus C P. Sorry, there is another P here. So A plus CT minus FT B plus DT. And this is A plus C. So we can rethink about a projection B A B C D that maps, let's say P A B C D. So we can rethink about hook up a different projection that's like sending the parameter of the tube to this image, to the image of a twisted projection at time t or at height t. And this, if we ignore, let's say if we ignore the b coordinate, or the fixed b coordinate, so we get a projection of the form A plus C T minus F D times F T times T minus D times. So for each T, this part is like an orthogonal projection. And once T is fixed, since B is also fixed, then this is just a translation of the orthogonal projection. And we also know that this set has to be small because for any A, B, C, D, E contains a lot of tubes, right? E contains all our tubes in our set of tubes. For all A, B, C, D, all the parameters of our tubes, this projection image is really small because it lies in AZ. And this is the last projection theorem that's going to be helpful. Oops, sorry. Just 1 minute. I'm going to end very soon. This is A, B, B, dot product is 1, 3, R, F, 3, B. And this is a projection in R3. And the direction of this curve is here. This is the direction of 1, 3, T, T. So we said that for Marstrom's projection theorem, for almost every point, for almost every directions, this projection image is large, and then all we want to show is that our AZ has a large dimension, and we have a lot of tubes, so we have a lot of ACD. So as long as we can one T that the issue is that here we do not have access to all the directions. Instead, we only have access to some curve. And that is a restricted projection, and that is where we use the f that f is C2. So first of all, f is C2, and also one can show using the Wolf axioms that the first derivative of f cannot vanish. So once we have that two information, this curve becomes a non-degenerate C2 curve. And there's the work of Praman, Yang, and Dart, and also some joint work with Larry Guth and Dominique Lafave, and also Sherman Gan, Sherman Guo, and Barry Harris. We show that if this is a non-degenerate C2 curve, for almost every direction, for almost every point T, this projection keeps the dimension of AC, the collection of ACD, and that's the end of solid. And this really uses that this is a C2 curve because we need to use decoupling in our version of the proof. Put decoupling for C2 curve. Thank you. Thank you.
Thank you.
Yes.
Can you maybe, as a teaser, is it easy to explain very fast why the sticky case is good enough to, I mean, obviously you're going to rely on the fact that you know how to do the sticky case. Is there an easy way to explain why the sticky case is already very representative of the general case? Or are you going to reduce the proof of the general case to the sticky case? Or?
Yeah. In the last lecture, I'm going to reduce the proof. Uses this as a black box and then show
Really,
how to.
box.
Yeah.
And then the extent to the general.
Yeah.
Means that the sticky case is already. So should we understand that most configurations are in the sticky case, or is it a different argument?
I think most of configuration are not sticky, but the extreme of configuration has to be sticky, and that's what we proved in our last paper.
Yeah, no further questions. But we'll be on tomorrow with the passage to the. Thank you.